Hello students, today you're going to learn about acids, bases and indicators. Lesson objectives: by the end of this chapter, you should be able to define an indicator, an acid, a base and pH, prepare and use plant extracts and bases, use indicators to identify acids and bases, state properties of acids and bases. Name the uses of acids and bases. State and explain the effects of acids. Introduction. Some foods are sour while others are bitter. The sour taste is due to the presence of acids, whereas the bitter taste is due to the presence of bases. Examples of substances that contain acids are citrus fruits and sour milk. Substances that contain bases include antacid tablets, toothpaste, and wood ash solution. Using taste to classify substances as acids or bases is not an accurate method. There are, however, substances which shows different colors in acids and in bases. These substances are called indicators. Now we are going to learn about how to make a universal indicator using a flower extract. So this is the procedure. Crush the flower petals provided using mortar and pestle. Add a small amount of ethanol or propanol. Continue crushing until a deep colored solution of the extract is obtained. Decant the extract into a beaker or a boiling tube. Place 2 cubic centimeters of each of the following substances into separate test tubes and label appropriately: hydrochloric acid, sodium hydroxide, sulfuric acid, potassium hydroxide, lemon juice, orange juice, lime water, wood ash, baking powder, and sugar. Add 2 to 3 drops of the flower extract into each test tube. Classify the substances in the test tubes as acids or bases and record observations. So according to the observations, you're going to get solutions of hydrochloric acid, sulfuric acid, orange juice, and lemon juice give similar color changes with the same flower extract because they are all acidic. Then lime water solutions of sodium hydroxide, potassium hydroxide, wood ash, and baking powder give a similar but different color. Water and sugar solution has no effect on the flower extract because they are neutral substances. So we are going to talk about commercial indicators. These are indicators that are commercially produced or commercially made. So the first one we are going to talk about litmus indicator. A litmus indicator is red in an acid, blue in a base, and retains its purple color in a neutral solution. So we learned that neutral solutions have no effect on an indicator. Litmus indicator is one of the commonly used commercial acid-base indicators. The indicator is also available in paper form as litmus paper. Other commercial acid-base indicators include phenolphthalein, and methyl orange. Phenolphthalein indicator is colorless in an acidic solution, pink in a basic solution, and colorless in neutral solution. Methyl orange indicator is pink in acidic solution, yellow in a basic solution, and orange in a neutral solution. The colors obtained when the indicators used in the experiment are added to acids, bases, and in neutral solutions are represented in a table below. So this table shows the color of litmus in an acid, in a base, and in a neutral solution. So litmus is red in an acid, it's blue in a base, and it's purple in a neutral solution. Then phenolphthalein in an acid, it's colorless. Then it's pink in a base, and then it's colorless in a neutral solution. The last one is methyl orange, which is pink in an acid, it's yellow in a base, and orange in a neutral solution. Then we're going to talk about various solutions classified as acidic, basic, or neutral. So neutral solutions are solutions that doesn't have any effect on indicators. Basic solutions are solutions that show different colors when placed in different indicators. Then acidic solutions, we have hydrochloric acid, then lemon juice, then sour milk, ammonium sulfate, then carbon 4 oxide solution. Carbon 4 oxide solution forms weak carbonic acid, so it's a weak acidic solution. Then we're going to talk about the basic solutions. These are soap solution, wood ash solution, baking powder, anti-acid tablet solution, and toothpaste, among others. Then neutral solutions, we have water and sodium chloride, among others. Next, we are going to talk about universal indicators and the pH scale. The acid-base indicators discussed so far provide no information about the strength of an acid or a base. Some acids are strong, while others are weak. So as I've said, some acids are strong, while others are weak. Likewise, we have some bases are strong, while others are weak. Now, the universal indicator is a mixture of several indicators. It exhibits a range of colors in acids and in bases, depending on the strength of the solution. These shades of colors are related to a continuous acid-base scale called the pH scale. And the pH scale has values that range from 0 to 14. So the pH values of acids The pH values of acids range from 0 to values just less than 7. So values below 7 are acidic. Solutions of sulfuric acid, hydrochloric acid, and nitric acid have pH values which range between 0 to 4, and therefore we classify this as strong acids. or we can call them commercial acids. Then lemon juice and ethanoic acid have pH value which range between 4 and 7. Then these are weak acids. As the pH values decreases from 7 to 0, the strength of the acids increases. Distilled water in sodium chloride solution have a pH value of 7. They are neither acidic nor basic and are neutral. So neutral substances are substances that are neither acidic nor basic. They do not exhibit any acidic properties or basic properties. The pH value of bases range between 7 and 14. Solutions of ammonia, calcium hydroxide, and sodium hydrogen carbonate have pH values between 7 and 10. They are weak bases. Solution of wood ash, soap, and sodium hydroxide have pH ranging from 10 to 14. They are strong bases. Next, we're going to talk about the properties of acids. So, when dilute acids are added to zinc, magnesium, aluminium, and iron, bubbles of a colorless gas are evolved. The production of bubbles of a gas is referred to as effervescence. The gas produced is hydrogen gas, and the gas is tested using a burning splint. A mixture of hydrogen and air burns with a pop sound. This is the test for hydrogen gas. When dilute sulfuric acid is added to zinc granules, hydrogen gas and zinc sulfate are produced. The reaction can be represented using a word equation. So in the word equation we have zinc plus sulfuric acid, which will give zinc sulfate plus hydrogen gas. An acid is a compound that reacts with metals to form a salt and hydrogen gas. As we've seen, zinc is a metal, sulfuric acid is an acid. When they react, they give out zinc sulfate, which is a salt, and hydrogen gas. Next, we're going to talk about action of acids on carbonates and hydrogen carbonates. When carbonates or hydrogen carbonates are added to dilute acids, effervescence occurs. Effervescence is the production of bubbles, which signifies the production of a gas. So when hydrogen carbonates or carbonates are added to dilute acids, effervescence occurs as the solid is used up. A colorless gas is produced, and the colorless gas produced is carbon dioxide. Acids react with carbonates and hydrogen carbonates to produce a salt, water, and carbon dioxide or carbon dioxide. The following word equations represent some of the reactions between acids and carbonates or hydrogen carbonates. So the first equation is sodium carbonate plus hydrochloric acid is going to give us sodium chloride, water, and carbon dioxide gas. Next is calcium carbonate plus nitric acid is going to give us calcium nitrate plus water plus carbon dioxide. Then Next is copper carbonate plus sulfuric acid is going to give us copper sulfate plus carbon 4 oxide plus water. So we've noted that when acids react with carbonates, they give out a salt plus water plus carbon 4 oxide. Here are the general equations of hydrogen carbonates and carbonates reacting with an acid. So as I've said, an acid plus a carbonate, it will give a salt, water, and carbon 4 oxide gas. Then an acid plus a hydrogen carbonate, it will also give a salt, water, and carbon 4 oxide. So the reaction between sulfuric acid and calcium carbonate stops after a short while due to the formation of an insoluble layer of calcium sulfate, which stops further reaction. So as I've said, the reaction between sulfuric acid and the calcium carbonate stops after a short while due to the formation of an insoluble layer of calcium sulfate, which stops further reaction. So calcium carbonate plus sulfuric acid, we're going to get calcium sulfate, which is a solid, water, and carbon 4 oxide. And when you want to detect the presence of carbon 4 oxide, you bubble the gas through lime water or calcium hydroxide. So upon bubbling the gas through lime water, a white precipitate will be formed due to the formation of insoluble calcium carbonate. And on further bubbling, the solution will turn to colorless due to the formation of a calcium hydrogen carbonate, which is soluble. So next we're going to talk about reactions of acids with bases. So when acids react with bases, this reaction is called a neutralization reaction because acids react with bases to form salt and water only, and salt and water are neutral solutions. Yeah. So the following are the word equations for the reactions between some metal oxides and acids. So all oxides and hydroxides of metals are bases. We should note that. So calcium oxide reacts with hydrochloric acid to form calcium chloride, which is a salt, and water. Zinc oxide, which is a base, reacts with hydrochloric acid to form zinc chloride, which is a salt, and water. Magnesium oxide, which is a base, reacts with nitric acid to form magnesium nitrate and water. So again, we're going to define a base as a substance which, when reacted with acids, form salts and water as the only products. Metal oxides, metal hydroxides, and ammonia solution are bases. Next, we're going to talk about properties of acids. And as we can see, acids, as we said earlier, they have a sour taste. Then they have pH values below 7. They turn litmus paper red, or you can say they turn litmus red. Then they turn phenolphthalein colorless. They turn methyl orange pink, and they react with bases to form salt and water only. They react with carbonates to form salt, water, and carbon 4 oxide. Then they react with metals to produce salt and hydrogen gas. Next, we're going to talk about properties of bases. And bases, as we said earlier, have a bitter taste. They have pH values above 7. They turn litmus paper blue. They turn phenolphthalein pink. And they turn methyl orange yellow. And they react with acids to form salt and water only. Next, we're going to talk about uses of acids. Carbonic acid is used in aerated drinks to enhance taste. Hydrochloric acid is used to clean metal surfaces. Sulfuric acid is used in car batteries, manufacture of fertilizers, etching of metals, manufacture of paints and detergents. The nitric acid is used in the manufacture of dyes, paints, explosives, and fertilizers. Ethanoic acid and citric acid are used as flavor in foods. And then we are going to talk about uses of bases. Then lastly, we are going to talk about uses of bases. And magnesium oxide and hydroxide is used in the manufacture of anti-acid tablets and lining of furnaces. So the anti-acid tablets made by magnesium oxide and hydroxide are used to neutralize the hydrochloric acid produced by the stomach. Next, we are going to talk about calcium oxide and hydroxide. So calcium oxide and hydroxide is used in neutralizing soil acidity and industrial wastes, making cement and concrete, and it's also used in the manufacture of toothpaste. I'm going to talk about sodium hydroxide is used in manufacture of soap and as a degreasing agent. Lastly, we're going to talk about ammonia solution, which is used as a degreasing agent and is also used in the manufacture of fertilizers and in the manufacture of nitric acid. So this is all about acid, bases, and indicators.